this white paper update? Would you?
Okay, well, glad to see that there are still people here on the last day. It's been quite a week. I've really enjoyed the talks this week so far. This morning, we're going to kick this off a little bit with an update on what's going on with the astronaut class. As many of you probably applied, but the 2017 selection is starting to go through the process now. So we are in prep for getting ready to design the training curriculum across the board that will start as soon as they are selected and announced. So what I'll talk today about is specifically the geology, geoscience training that we'll be doing, with a little bit of background on what we've already done in the past. So a little bit of introduction. As you all know, the shuttle was decommissioned, the program, few years ago, and the most recent classes, the 2009 selected class, the 2013 selected class, and this class in 2017, they don't have shuttle training, which was the dominant piece of their training block in the schedule. So what that did was opened up time for other things in there. So now some of that was going over to Russia, learning how to fly with the Russian systems, learning how to talk in Russian so that you could actually communicate with them. So there are plenty of things to fill that time slot. A group of folks also got some of the geology training in there. Prior to this time, the astronauts had gone through training, a small amount of Earth observation training from shuttle and ISS. So they had a handful of hours, and usually that was related to them after they were selected for flight. So they didn't really have a dedicated science training, and especially geoscience training, that was built into the program early on. So these classes that are coming in now, some of their job descriptions, again, since they're not flying stations, maintaining ISS, testing the new flight hardware that's coming online over the next few years, and running the science facilities. So again, that's ISS, but that's also all the experiments that are sent up there. And sometimes, that's just, you get the experiment and pull tab A and do this and let the ants loose and stuff like that. So it's a lot of learning how to follow the instructions that are written up with their tests. So we've talked a bit throughout the week so far about NASA's long-range vision, eventually, seen the squid chart a few times, getting humans to Mars. But in the meantime, as we're working our way there, we're going through this proving ground phase, which can involve the moon, asteroids, and the moons of Mars. So without a dedicated geological target with funding in a program that says those astronauts are going to do operations on the surface, we did have to kind of defend this training program a little bit. And if you're not going to the moon, you don't have an Apollo-like mission to go to the moon, why should we teach them about the moon? Why should we teach them about geology in general? And so we've worked with a community of folks that do this, and I think Jim actually said it very eloquently the last cycle we were doing this. He said, the people we're training right now, they might not be the ones that actually walk on that surface, but they might be the ones who are higher up in the chain of command when that happens, and they'll be making the decisions about how it happens. So what we're really doing is learning about training the operational mindset so that when this group of folks is moving forward and they're helping plan exploration of the solar system from the astronaut level, they understand science and they understand what we need from them. Jim's given talks on this here at Survey. Several people have talked about this. I won't talk about it a whole lot, but we all know about Apollo. We landed astronauts on the moon. They did a tremendous job collecting samples, acquiring observations. There's a lot of training that went into that. And again, Jim was involved in that. This was just an example of some of the data that Dean Epler mined out, and to show how much training went into this. For Apollo 15, this is the total amount of hours that were put together on different types of training related to the science that they would be working on and the geology. It accumulated to about a little over 1,000 hours per individual. But they also received specific training on deployment of instrument packages, things like that. So this is, a kind of a low number on training related to exploration on the surface of the moon. All this data has recently been published in Special Paper 626, Herculean effort by Dean Epler to get out what was known unofficially as the Finney Report. If you get a chance to get a hold of this, check it out. It's a tremendous volume. One of the cool things that Dean mined out of that data was how much time they actually spent in the field. And so he had a few charts that are in that book and in a couple other papers that we've put together in the last few years. I tried to sum this up. Between 1970 and 1972, 59 different field experienced geologists trained the Apollo 15 and 17 crews. And we summed up the numbers. That came down to a 10-to-1 individual scientist to crew member ratio. So we give this talk to teachers. We like to say, that's the opposite of the ratio you're used to, right? It's one of you versus 10, 20, 30 students. But it just shows how much effort was put into this training. Among these individuals, there were 375 individual trips that were paid for to get people out in the field to 27 different field sites. And this didn't only involve the Apollo crew, but all of the folks in some cases that would be involved in the missions. So recently, League was asked to put together a report in preparation for the 2017 class being selected. This is called the Geologic Astronaut Training SAT, League GATSAT. And we had a few observations here. This is an image from training of the 2009 class at Warford Ranch. You can see the groups of, usually we have one instructor and two astronauts out in the field working together. But a few of the high-level points. Curriculum based on synthesis of planetary and terrestrial geology is a beneficial combination and should be continued. It should be continued regardless of whether or not we have a destination, whether or not there's a program that says we're landing on Mars or we're going to a near-Earth asteroid or whatever. And again, this group had members from the training groups that helped over the last several years. It also had folks from outside of that, geologists from outside of that group, and also had members from the astronaut office itself. So this was a effort including all of those aspects to try and put these points together. The geologic training should involve not only the astronauts, but again, all of the personnel who will be involved in this. So you don't just train the astronauts how to do the geology. You want the person on comm. You want the engineers who are building the equipment to understand what they're going through when they're out there on the surface doing the geology. A really important point for us was that the geology field training for 2013 class integrated what's called space flight resource management. We had to fight pretty hard to keep the training program in. This was a huge effort again by Dean Epler and many others to not have the whole thing canceled, again with the main criticism that we aren't going anywhere. We don't have a program to send our humans anywhere. So all the other groups that wanted more time for their individual training were pointing at geology and wanted it out. And so what we did was, instead of trying to say, well, here's how we train for geology and we want you to just accept this, we worked with the astronaut office and tried to understand what were their needs. What were needs they had that weren't quite filled by the current training curricula from the other groups. And one of the things that we could provide was this SFRM, which goes beyond just basic geology, but it's about team building and working together as groups out there, which is very important to them. So this was the one main hook that got us through in 2013, and now it's really well integrated in with the other things that are going on. So it's really what we're standing on to stay alive here. And the important point now moving forward at this point is that we are responsive to what the astronaut office is asking of us. If they need something, we work to try and build it in. The astronauts go out on what's called NOLS training when they first get selected, so basically survival training. After that, they don't really have any outdoor training. So we're the one opportunity for them to really continue and build those team building efforts out in an environment other than simulated places like the neutral buoyancy lab or tests like that. Dean recently put together a paper in GSA Today. It's actually coming out next month, so keep your eyes up for that. So how does the training work right now? We basically break it down broadly into three different things: teaching and field camps, field assistance, and integrated analog tests. And our approach is basically to take any opportunity we can to get science and geology into the discussion with them. So whatever the opportunity is, if we can find a way to involve geoscience in that discussion, we take advantage of it. Another important point is that this does not only involve training them during their candidacy, but it's also starting to become something they do to back train senior members in the office. So again, this training started to come up online again in 2009. There are a lot of astronauts who were in the office prior to 2009 that did not receive this. We are now starting to engage them and get them kind of this back training, if you will, to bring them up to speed. So again, this concept of if you're not going anywhere, we don't need the geology training. So one of the things we had to do was be very delicate about how we talked about the planets, specifically about these potential targets. So in a lot of cases, the science training that was provided to them, we started out kind of from a historical context. So, you know, folks like Jim, along with some of the prior astronauts like Dave Scott and Jack Schmidt came in and really kind of set the tone for them. You know, this is where this comes from. This is why you learn this stuff, to lead towards successes like what we had in Apollo. And then they got some background training on asteroids and the moon and a little bit about Mars. And, you know, there are a number of people in the room who took part in that kind of training. And just for your awareness, this group is called, they named themselves the 8 Balls. They're the 2013 class. So then we started to get into the bulk of the classroom training, which was very discipline focused. And this is where we basically just start training on individual topics. So, you know, David talked about impact cratering, how to recognize it, how to study it in the solar system by thinking about what we have on Earth. Structural geology, geomorphology, volcanology, and petrology. They get these topics and they're learning them. It's a little bit of a fire hose. And again, they're not graded on this. This is not a requirement for them, such as learning Russian. They must understand Russian at a certain level to advance out of candidacy into being a full astronaut. They do not need to possess a certain knowledge of geology. So we have to be delicate in the way we present this material to them. But the way we brought this together, we had a phrase called outcrop to orbit. So we wanted to make sure everything that they saw was linked back to something that they could see from ISS, because this was one of our hooks into what was already existing, the Earth observation. So I'll give you a few examples from what I taught, which was in the volcanology section. You know, when they're up on ISS, they're running experiments, they're keeping the ISS running. They have some free time. You know, there's a window there. They can go look out the window. They're not required to. They don't have to do that. So I just gave them a simple set of rules that I gave them was look out the window. I want you to know how to identify volcanoes. I'd like you to be able to acquire images of them. And then the key part is being able to describe what you see. That's the observational part to the science we're doing. So we talked a lot about, you know, what does a volcano look like? How do you know that that's a volcanic setting from orbit? What are different about volcanoes? Something like Kamchatka versus Pu'u'o. They're very different volcanoes. So most of what we try to talk about started with observation and then try to explain why those observations relate to some kind of process that an experienced scientist like ourselves would be able to interpret from the descriptions that they give us. So we went into a lot of detail about how to make observations. So an example here, this is Cleveland volcano in the Aleutians. You know, we dispel the concept that every volcano on Earth has an observatory on it. In fact, very few do. You know, so we don't know about a lot of these volcanoes. We learn about them from geophysics. Sometimes we go to visit them. But a volcano like Cleveland, you know, it's a bad place to go put a camp, and it's not easy to get to. And this was an ISS image taken of Cleveland during an eruption, the only images we have of that eruption. So we drive that point home that you have this really unique perspective. Now, for me personally, and evidence that this was setting in with them and working, Christina, one of the members of the 13 class, emailed me at the beginning of 2015 and sent me this picture. And she said, I was flying in Nicaragua and I see this volcano out the window. So I took a picture of it out the window and I wanted to show it to you because your mantra was running through my head. Look out the window. So I had my face on the window. I saw the volcano, so I took a picture of it. And she said it was steaming a little bit and, you know, it looked to me like it might be erupting. And I said, well, you know, that's Momtob, first of all, because it has this really distinct channel. And I know that one, but it hasn't erupted since a long, long time ago, over 100 years. So it might be steaming a little bit, but I doubt it's going to erupt. Well, she totally called, made me look like an idiot. A few months later, it erupted for the first time in over 100 years. So I said, Tina, you were right. Good observation. You saw that it was preparing for an eruption. That's exactly the kind of thing we want to get. This stuff's contagious with them. You know, if you get one of them good at it, if you have 8 people and only one of them cares in the astronaut groups, that one that cares is the one you target, you get them hooked, and they're all super competitive. As soon as one person shows an interest to get it done, all of a sudden they're all involved, and it's really impressive thing to see. This is our example of success from orbit, the Bleacher volcano. As we were told, as they went by on one orbit, they noticed that there was something in the atmosphere, a little hazy. Over that orbit, got the camera out, got ready, we're in the cupola looking out the window, and they got some of the most impressive images of a volcanic eruption from orbit that we have from ISS. The field camps. So this is where we bring together the outcrop to orbit. So they get to understand what the Earth looks like from up there. Now we go and get their noses on it, right down on top of it. You know, here's an example, David Kring leading a group. In this case, this was actually senior members of the office when we were requested to back train a few of the senior members. So, you know, get them out there. Impact craters, you know, we know what they look like on images. But this really drives home the point about what it's like to walk in them. Can you do this in a suit? Think about doing this in the suit that you wear in the neutral buoyancy lab. That kind of stuff really brings it together for them. Here's just an example from the 09 class. We showed them images of you know, dike swarms and dike features related to volcanic vents from orbit. They can get right down on the ground. We get their nose on a dike, so they can really see what these structures and features look like. So the other aspect of this is we call field assistantship. So a number of us in the training group, you know, we do field research. We go out and we do our own research. So one of the things that we build in now is we'll bring an individual out with us. And I like to think about this as where they really complete the cycle of training. So they get the classroom, they go on field camps, but for all of you who've been on field trips, you know that a field trip is a field trip, right? No matter how hard the teacher tries to make it seem like a brand new thing, you know they've been there before. This is a place they've probably taken multiple groups. We get them out there in a very brand new setting. I like to point at this picture. This is Brent Gary, Christopher Hamilton, and myself on a lava flow in Hawaii. I like to say that they know how to walk the walk. They're better at walking the walk than we are in many cases. But here's where they really learn to talk the talk. So they get to see 3 scientists totally disagreeing on what their observations mean, building the hypotheses in real time and developing them and testing them while we're in the field. That's where they really start learning how to talk to us and describe what we need to hear to be able to understand the geology. The integrated analog tests are another aspect. NEMO is actually active right now. They just splashed down a few days ago, so they're underwater. But these are times where we're really testing the hardware in an integrated sense to see if it all works and does what we want. You know, engineers from here build this, engineers from here build this. Then they bring it together and, you know, slot A doesn't fit in tab B very well. You'd only learn that by actually going through the process. But in so doing, it's a good chance for us to get some more geology put in front of their face and to talk about it a little bit. And also, there are crew members over in the ESA Caves analog test right now, working with the folks from ESA. So they get out there and they're exploring in a hazardous environment, real environment, doing science in real time. And again, this picture was just released yesterday. This is the NEMO 21 crew, and I think they have 3 astronauts on that crew right now underwater. So, you know, they're in there doing it. So we got astronauts in orbit, we got astronauts on the seafloor, we got astronauts in caves. We're getting the science in front of them and helping them to learn about it. So current planning, it's underway for the 17 class through the ASCAN working group at JSC. Again, we're working with the astronaut office to start designing the geoscience training workflow. So we've got a huge timeline. It seems like a lot of time, but when you start filling it in with everybody's blocks, it's filled up really rapidly. So we're trying to be ahead of the stream. We don't know exactly how many are going to be selected. So we're kind of contingency planning for, you know, big groups, little groups. How are we going to put this together? Again, the big important point now is this flexibility to enable responsiveness. So we've offered situations like if we are out in the field and you have a crew member who's lagging behind in their comm skills, we can easily evolve what we're doing into a setting where they have to communicate through radios with each other. And you can pair them up with a senior, someone who's a pilot with someone who's not a pilot, so they get that experience. So this is what I mean by the flexibility and addressing what they're asking for. So what is the payoff? Well, we now have a large number of geologically trained astronauts who are flying fairly regularly. I don't know how many of you follow the ISS or individual astronauts on Twitter or Facebook, but they are pumping out really excellent images. Again, I'm a volcano guy, so show you some of these. Jeff Williams up there, he just posted this about a couple weeks ago. Mount St. Helens, great shot from orbit. Really tremendous example. Yesterday, he posted this of Kilimanjaro. I mean, they're seeing the stuff. They've listened to what we say. They're looking for it. They're getting these images out. And they're pretty responsive to the requests we make. For instance, when we were out with David Kring's group last year doing graduate student training in El Malpais, Kjell Lindgren was on orbit. I emailed him. I said, hey, we got these students out here with Survey. Took a picture while we were out there. It was really cool for David and I to be able to show these students, hey, guy on orbit took this picture last night while we were in the field. So that kind of thing. So that's what's going on right now. I just want to conclude with one slide. This is an image taken from ISS last week, and just want to drive it home to you all about why this is important, because these people are going to be the ones that do some of the cool things that you're thinking up and talking about right now. They're getting ready for it, so much so that they're even looking at the moon. This had to be an awkward angle to get the camera to get that picture, but it's tremendous. And here's the website. The images are up there almost instantly. Use it. These folks are taking pictures. You can also put requests in there. You have a field site, put it in there. Ask them to take pictures. But again, I just thought it was really fitting. This was last week they took this picture, and there it is. All right, thank you.
Thank you, Jake. That was much more interesting than the paper I erroneously attributed to you when I... Okay, questions?
Jake, it's somewhat disconcerting, I guess, the disconnect seems to be between the astronaut office and the opportunities in proving ground and eventually going to Mars, even from orbit, as you and David and I all talked about yesterday. With the surface telerobotics, there's real geology that can be done from orbit. And so this kind of training is important now, even though the astronauts may not be putting boots on the ground immediately, although I suspect we will in a few years. So, how do we overcome that disconnect and really get that technology across? Because I think we're all challenged in trying to get NASA headquarters to really completely embrace this and to fund it for further development.
Yeah, the first thing I can say is that they are aware of that. And in fact, the specific example you're talking about, we had discussions about that during that LEAD GATSAT. We're trying to find the hooks that make sure we stick around, we don't get canceled for the next class. And what's relevant to what they're doing now? We talked about the proving ground, and why would looking at a sample be relevant? Well, they may be operating a rover that's deployed some antenna assets and then goes on to look at samples directly. So I understand your concerns, and unfortunately, the best I can tell you is we're working on it. But coming to these meetings and saying that stuff in front of folks like David, me, Paul, Sarah, people who are involved is right now probably one of the best conduits.
Hi, that was fascinating, and this interface between science and the engineers is just so critical. 5 or 6 astronauts now. Is this working? Okay. 5 or 6 astronauts now have participated in the Antarctic Meteorite Recovery Program. Mm-hmm. They've done it on their own nickel. They've done it in their spare time. But every one of them has thoroughly enjoyed the experience. And one of them actually said this was the closest thing to being on a mission. Mm-hmm. So I know there's a danger here of us all promoting our own interest through this poor bunch of guys who've got other things to do. But I just wonder if, at your end of things, whether you've heard any thought of perhaps using that as an option for training these astronauts and getting the scientists and the engineers closer.
I can't speak specifically to how that program is integrated in an official sense. What I can say is it's not a common thing for them to be able to dedicate that much time to being away from the office, which makes it difficult, which is why they do it on their own dime. But that points to the fact that they recognize internally how valuable those experiences are. I mean, the caves, the Nemo, Antarctica, it's all about getting the experience. And one of the things that I've been told is they like to push them into uncomfortable situations.
Yeah.
So any chance they get to put their crew members through the ropes is something that they like to try to get into. So, I can't speak for what the astronaut office thinks about that. That would be my guess, but I also know that they recognize it as a valuable experience.
Paul, you'll be the last question.
So it's just a comment and following up that. So I can't speak for the astronaut office either, but being at Johnson Space Center and knowing these astronauts that have gone on those field trips to Antarctica, it's something that is very valuable. One of them actually is in a management position now and is recommending that a crew member actually go on these expeditions, and because it is very similar to going on a spacecraft mission and dealing with a harsh environment and yet doing science. And so I think we're going to see that this is going to be part of their program, at least encouraged a lot more.
And Paul just reiterated that really important point, which is, Jim mentioned, is when we first start talking to them about this, it was just kind of, yeah, maybe. But the more that get these experiences, they move up into management positions, and then they have experienced it, they recognize the value of it, then they're able to be advocates for what we're trying to do within the office. And so it's a slow process of, working it in, but I think it's working. And all of these experiences are immensely valuable.
Thank you, sir. That was good.